Howdy. All right. We're going to talk about calculating area under a curve. And the setup is this. Suppose you have a function f that's bigger than 0. And you want to know, over some interval a to b, what is the area underneath that curve? Okay. All right. Well, we know how to do it for rectangles, triangles, circles, we've been taught, but how do you do it more generally? Well, it's really quite a brilliant idea. The idea is this, to say we can't figure it out exactly, but we can approximate it with rectangles that we know the area of, and then take better and better approximations, namely, in the end, take a limit to get the exact answer. All right? So the setup is this. You're going to take your function f over your interval. You're going to approximate the area with rectangles. Add up the area of all those rectangles, and it will be close to the area under the curve. And then if we can find ways to let sort of the thickness of the rectangles go to 0 eventually, then we can try to get an exact answer. All right? Now to set all this up, well, we need a lot of notation. So let's go ahead and start. First of all, let's say we've got this function f here from a up to b. We care about the area under the curve. What we're going to do first of all is develop notation for splitting this interval up into pieces. So we'll let x0 be the first part. And then let's say we have n intervals. So if we want to have n intervals with equal thickness, then the thickness of each of those should be b minus a divided by n. And then we just move over to x1 here, so that this has width delta x. So in other words, x1 will just be a plus delta x. And then we move over to x2. So this interval here will be delta x, so that x2 is a plus 2 delta x. And you keep doing it this way. So you see in general, you have all these xn's, and in general the xj will just be a plus j times delta x. And this will be the n minus first one, and then b will be the very last one, x sub n. All right. All right, then we need to get the rectangles, and you can do this in lots of ways. And we'll see with Riemann sums later on a general way to do it. For now, let's just always grab the right-hand side and make a rectangle using this right-hand endpoint. So the height here will just be f of x1 for the first rectangle. For the second rectangle, the height will be f of x2, and so forth, until we get to the last rectangle, and that guy's height will be f of x sub n. Then, if you want to know the area under the curve, that'll be approximately the sum of the areas of the rectangles. Okay? So this would be the first rectangle and so forth. So the first one, the area is height times width, so the height is f of x1 and the width is delta x. For the second one, you get f of x2 times delta x, so forth, until the last one, which would be f of xn times delta x. All right, so that's the long form. The short form uses the summation notation. It's the sum from j equals 1 up to n, f of x sub j times delta x. So that will be the sum of all the areas of the rectangles, which, as long as delta x is small, will be darn close to the actual area under the curve. Okay? All right, so we give a name to this. It won't matter in the long run. It's called the right-hand approximation R sub n. It's the sum from j equals 1 up to n of f of x sub j times delta x. And the point is simply that R sub n is approximately the area under the graph of f. Okay? And of course, as delta x goes to 0, the answer should become exact. All right, but we won't worry about the exactness now. We just are going to do the approximation. All right, that's it for the right-hand approximation of area under a curve using rectangles.